Okay, so we're in the part of the syllabus about structure determination, and there's a time right now for us that we could pick a couple of different types, but it just so happens that the Organic Chemistry 2 people have started to do NMR. And so we're going to do NMR also. And in fact, the worksheet that's in front of you is an Organic Chemistry 2 worksheet. If you were previously in Organic Chemistry 2, you did not get this particular worksheet. So it's going to be new for most of you. All right. Nuclear magnetic resonance. We'll talk about theory in regular lecture tomorrow. We're going to use this time to just do some problem solving. But the nuclear means one type of nucleus at a time. And the type of nucleus that we're going to spend our time looking at right now is the hydrogen nucleus, because the hydrogen nucleus contains only a proton. This is also known as proton NMR. Okay. 3 pieces of information. Chemical shift. Chemical shift runs from 10 to 0, really reading this way. And occasionally it goes up to 11 because aldehydes live there. What we measure on this scale, and it's really a frequency scale, we'll talk about it in regular lecture at some point later, but all we're doing today is solving problems. If you are to the left of this scale, you are near some form of electron withdrawal. Name the 2 forms of electron withdrawal. Electronegativity is 1. That's inductive effect. That's the -I inductive effect, which is electronegativity. What's the other form of electron withdrawal? Matt, what's the other form of electron withdrawal?
You were just talking about in class.
Yeah, how can I recognize an electron withdrawing group?
By looking at what if it's double bonded to the ring.
If an atom is multiply bonded to an electronegative atom, it's an electron withdrawing group by resonance.
I should know that. I wasn't really listening. So I'm here now.
Are those just like tick marks in front of them, or is it hard? Sorry. Are those like from the I and the R just tick marks?
That's negative.
Oh.
If it's plus I, then you're on the left-hand side of the periodic table and you push electrons. If you're plus R, then you donate electrons by resonance. How would we recognize an electron donating group?
The atoms double bonded to the ring directly.
Electron donating groups have lone pairs of electrons. Electron withdrawing groups are multiply bonded to electronegative atoms. So proximity to electron withdrawal pushes my signal this way by a process called deshielding. We'll do the theory tomorrow. Today is application, tomorrow is theory. Chemical shift tells me frequency, tells me how close to electron withdrawal I am. The other thing that an NMR gives me is integration. If I have a signal and the signal is this big, And then a bit further down, there is a signal that is this big. The integral, the area under the curve between these, well, that could be 1 to 6 or something like that. The area underneath the curve tells me how many equivalent hydrogens generated the signal. So one of the things that we'll look for in a structure is how many of the hydrogens are in unique positions and how many of the hydrogens in the structure are equivalent. Like all 3 hydrogens in a methyl are going to be equivalent to each other. So methyls give rise to signals that have an integration, a size, a physical size to the signal that has 3 hydrogens in it. And then the big one that's going to help us put the puzzle together is multiplicity. Multiplicity is the number of lines in a signal. If a signal is subdivided into smaller signals, that's what's known as fine structure. And the multiplicity in proton NMR follows the n+1 rule. That if I'm looking, let's pick one. If I'm looking at that hydrogen, here in bromoethane, this hydrogen has 2 other hydrogens in equivalent positions. There is no difference between that one and that one and that one because this bond is allowed rotation, conformational rotation of 360 degrees. That one right there. So all 3 of those hydrogens are the same as each other, which means this part of the information. When I want to know about the neighborhood that this hydrogen is in, I find that it has 2 hydrogen neighbors. The circled hydrogens are not neighbors to this hydrogen because they're the same, they're equivalent. Its neighbors are on the vicinal carbon. They're on the neighboring carbon. And it has 2 of them. 2 plus 1 is 3, which gives me a triplet. That triplet is the signal for all 3 of the hydrogens that I have circled. The hydrogens that are in the square boxes, now there are 2 of those, they have 3 hydrogens as neighbors, and 3 plus 1 is 4. Oops. And so that makes a quartet. If we were to look at the NMR of bromoethane, we could predict what bromoethane looks like on a scale from 0 to 10. Because the methyl has 3 equivalent hydrogens. So its signal might be this big. I'm going to put some fine structure into it in a minute. But this methylene, CH2s are called methylenes, only has 2 hydrogens in its signal. So I have a 3 hydrogen signal and a 2 hydrogen signal. And 2 hydrogens, no, that's too big. I'm drawing this by hand. Might fill the space under this curve. 3:2 ratio, kind of, sort of. Okay. So I know the size of my signal depends on its integration. I know bromine's in group 7. That's my electron withdrawal. These hydrogens are close to the electron withdrawal. These hydrogens are far away from the electron withdrawal, which means my CH2 goes here and my CH3 goes there. This might be 1, this might be 3, something like that, making a guess. And then I put in the fine structure that these equivalent hydrogens have 3 neighbors. So I get a quartet there. And then these 3 equivalent hydrogens have 2 hydrogens as neighbors, and so that makes a triplet. And in the old days, you just had to believe. But in the 21st century, we now have Spartan on our iPads. And let's see if it knows how to do this. So pick some carbons. There you go. I have made an ethane, and then I'm going to pick a bromo. Probably won't know a bromine. Ugh, done that wrong. Two bonds. One of them is to bromine. And then, what am I going to do? I'm going to... It recognizes that that is a bromoethane. Let's see if it's in the database. Calls it ethyl bromide. Not great. And predicts that this is what the NMR of that molecule looks like. A triplet and a quartet. And the triplet is at about 1.3, and the quartet is at about 3.5. And I get the added bonus if I touch any of the hydrogens. I highlight where they appear in the spectrum. Okay. So we have a worksheet. Let's do some work. Yeah.
Can you explain over the area under the curve again? Why the triplet is bigger than the quartet?
In bromoethane, I have this gives rise to a signal. But it is the same as this. And it is the same as that because this bond is allowed to rotate 360 degrees. So, if I hold this up, because that bond is allowed to rotate, in fact, I might be able to do that. If I go back to the 3D structure, I think I can highlight a bond. There you go. No. I'm allowed to rotate that bond, which which I can't quite do, 360 degrees, which means they're all the same as each other. Okay? And if they're all the same as each other, then they all give rise to the signal. And there are 3 hydrogens worth of signal here. There are only 2 hydrogens worth of signal here. And depending on the vintage of the data that you're being shown, some of them write the integration in a little box underneath the signal. Some of them write them above. Or if you go way back, the integration used to, when it was ink plotters that generated the signal, you would have a second pen that would make a second pass and give you a sigmoidal curve, and you would have to measure how many little boxes, because it would be a graph paper. You would measure how many boxes high this was and how many boxes high that was, divide by the smallest number. And if this one came back to be 1 to 1.5, you would know, well, I can't have a half of a proton, so it has to be 2 to 3. Okay, let's do some work. So the first couple of pages are theory about integration, multiplicity, chemical shift, shapes of signals, and then how this exercise is different than the Organic Chemistry 1 exercise. We go into a little bit more detail. We're going to talk about molecules that are isomeric to other molecules, different classes of molecules that you didn't see in Organic Chemistry 1. And here's a couple of different looks at geometric isomers. They get tricky when they go aromatic. But you can see that the gap, this gap, the gap between 2 lines in a signal is given value J and is called the coupling constant. And if that value is big or if that value is small, can reveal information about the stereochemistry or geometry of the molecule that you're looking at. Okay, so question 1 is straightforward. Draw the structures. Question 2 is not particularly difficult. Question 3 is straightforward. And then when we get to being question 4, we start a discernible difference. And then 5, 6, and onwards, they're phrased in a more difficult way. They're not that particularly difficult. And then 7, 7 tells you what the possible answers are and has you track them down. Let's do sum of 3, because 3 is straightforward. You're given 6 spectra. They're very, very simple. And then you have some names of molecules, and you just have to match the molecule to the spectrum. Giving you the iPad. Yeah, you should try that. The iSpartan app is still, I think, less than $20. And can't tell you to buy additional material for the class, but it is super useful. Oh, so there's a chance that
It's not in the system.
yeah, because this is the cut down version. If it's not a recognized molecule,
Got it. Or something.
but that one is.
So it's.
So you could, with this device, with this software, cheat and just write all the names of all of the possibilities in and match them. And in cheating, hopefully you learn as you go. Because it does ask you to assign what's going on. So you have a, not a doublet and a triplet. Okay. If you touch the triplet, it should highlight the hydrogens that are giving rise to it. Yes, oh, yes. Perhaps the other way around. Touch the hydrogen.
Well, it's, yeah, it's highlighting more.
Oh, there you go. Yeah.
So just gonna highlight one.
Oh no, it's a group. They're a group. That is a signal that has been split because it has
Oh, that's right.
two
That's right.
hydrogens as neighbors. Therefore, it's been split into a triplet. So you can do this from forwards back. You can touch the signal, and it reveals those hydrogens are equivalent to one another, and they have one hydrogen as a neighbor. Therefore, it's a doublet. Or you could do touch the hydrogen and reveal NMR environment. Which one of those signals is furthest downfield?
The signal.
And the fact that there is only one hydrogen is because there are two chlorines attached to that carbon. So downfield means pushed to the left. Upfield, basically upfield is left alone. The act is pulling electrons this way. It's not really ever pushing, because there's not, unless it's carbons, pushing electrons that way. So our proximity to electron withdrawal was larger for the carbon, for the hydrogen that is on the carbon than it has two chlorines attached to it. Look at the effect of, if I'm a regular metal, I should be here. If I'm a regular alkyl, I should be there. So regular alkyls, 1.5. Where are your two signals in this spectrum?
Close to 4 and 6.
6. So the one that is next to two chlorines is all the way down at 6, and the one that is next to one chlorine is here at 4. That's telling you that direct proximity to electronegative atoms is a big deal. And we'll talk about the theory of why de-shielding exists tomorrow.
Oh, yeah.
Acetone is on that list?
Yeah.
Okay, you know what the structure of acetone looks like?
Yeah. It's a carbon dioxide.
Okay. Symmetry.
Gosh, it is a.
There's multiple symmetry operators here.
So it's a. Is it C2? Is that how you say it?
Yeah.
C2, and then it also is. Isn't E always a thing?
Yeah, there's always identity. So that molecule is has a mirror plane and also has a rotational symmetry right here, which means those hydrogens and these hydrogens are the same as each other.
So you
So you get one signal. There's one environment for hydrogen in this molecule. Integration of 6. Multiplicity tells you the number of lines. So if there is a spectrum on that sheet that contains just a singlet, then perhaps that's acetone. But the problem is, there are 2 spectra.
Because there's a bromopropane, which is also.
Okay.
Well,
What I would do is go to the build acetone in the, oh, you know what? So here's what we had to do. We had to go to a correlation table. There's a correlation table on the back page. And the correlation table tells you that if you are a regular alkyl group, in fact, you're a methyl, then you are right here at about 1 ppm. Do any of the singlets in your spectrum have a chemical shift of 1? No, because in acetone, see this? Matt, how do I recognize electron withdrawal?
Double bond.
The atom that the methyl is attached to is also doubly bonded to an electronegative atom. I am pulling electrons away from those methyls. The question is, to what degree? Acetone contains a ketone, which is a carbonyl. And on your correlation table, it gives you a chemical shift range of about 2.8. If you drew the molecule in Spartan, I'm sure that Spartan would agree with you. All right, so we know that this is electron withdrawal. That's an electron withdrawing group. And it managed to move the the methyl that should have been at 1 down somewhere between 2 and 3. Compare that to the previous example, which moved this hydrogen to 4 and that hydrogen to 6. Which is the most profound effect? Being directly bonded to an electronegative atom or resonance? Yeah. That's going to become important later, because you're going to have to make choices about this. This is an ester. And we're going to want to know what the difference between those two is. I have an ethyl group, I have an ethyl group. This ethyl, the methylene, is attached to the methyl and an atom that has no hydrogens. This methylene is attached to the methyl and an atom that has no hydrogens. This methyl is a singlet because it's attached to an atom that has no hydrogens. That methyl is a singlet because it is attached to an atom that has no hydrogens.
So chemical shift is dependent on.
But this, being directly bonded to an electronegative atom, is going to have more of a downfield shift than this being attached to an atom that displays electron withdrawal by resonance. This one gets pushed that much, and this one gets pushed that much. Okay, let's do something a bit more taxing. Let's look at question number 4. Take your pick. If you see signals at 7 ppm, chemical shift of 7, that's an aromatic ring. I've got 7 carbons, which potentially means 7 environments for hydrogen, but only 2 signals. So, yeah, something's repeating. There is some level of equivalence going on somewhere.
What about the signal at 0? Is that not one of them?
Oh, so at 0, that's an internal standard. TMS, tetramethylsilane. They dope the solvent with TMS. because, and then we set its chemical shift range to be 0.
So, did you say there are 3 signals or 4?
I see 2. Yeah.
Look, this guy right here. So those 2 separate ones?
Depends what your perspective is. Depends. So the question is, how many signals are in this spectrum? That is our standard. That's tetramethylsilane, so that one doesn't count. Then there is a signal here. That counts. And then, is this either 2 separate signals, or is that one signal with a very wide coupling constant? And it depends on your perspective, which in turn will depend, have you read this page? Benzene is, of course, flat because it's an aromatic system. So when we look at this particular hydrogen, is that hydrogen unique?
No.
No. What other hydrogen is just like it? That one. Is this one, so we know that this one is the same as that one. Is this one the same as that one? No. So we can label these as being different. This hydrogen, B, how many hydrogens as neighbors does it have? That's a doublet. And then this one, hydrogen A, how many hydrogens as neighbors does that one have? So that's also a doublet. But are we to assume that the view from A looking at B is the same as the view from B looking at A? No, they are different. So what we get is my signal is split into a doublet, and then each of those doublets is split into another doublet, and I get a doublet of doublets. This is different than a quartet. A quartet has 4 lines, but the peak heights go small, big, big, small, and the gap between them is the same. Here, I get same height, same height. This gap and that gap do not need to be the same. And in fact, if, I'll call those X and Y, if this group A and that group B are the same as each other, then everything's the same. If group A and group B are different but similar, let's say that was a methyl and this is a propyl, or that's a methyl and that's an ethyl, they're really similar. This doublet of doublets closes in. If I make this an electron withdrawing group and that one an electron donating group, then I get a great big gap between them. So this gap, this central gap, depends on how different those groups are. Look at your spectrum. How big is the gap?
3.4.
Okay. Doublet of doublets means you have a para disubstituted benzene. Para disubstituted benzenes are C6H4. If you subtract C6H4 from the formula in the question, it tells you what the other substituents can be. So I have C7, H7, Cl. Because I know that my para-disubstituted benzene, the central part, is C6H4, that means a carbon, 3 hydrogens, and a chlorine. Guess what your 2 groups are? Come on, it's not that difficult.
It's just a hydrogen on the others.
No. Something has to go in that box, and something has to go in this box. And we know that it's para substituted benzene because I've got my doublets of doublets. And the chemical formula for my unknown is C7H7Cl, and it looks like this. Yeah? Is that a singlet? That's a singlet. What's the integration on the singlet? If whatever goes in this box is a hydrogen, if whatever goes in that box is a hydrogen, then you no longer have a para substituted benzene, you have a mono-substituted benzene. So whatever this is, it's never a hydrogen.
So it's a methyl and chlorine that we use substitution for this.
This tells me there are 4 hydrogens on the ring. If I put a hydrogen in this box, there are now 5 hydrogens on this ring. So it's not a hydrogen. The integration on this signal is 3 hydrogens. Surely that's a methyl. A 3 hydrogen signal is a dead giveaway that that's a methyl. So C7H7Cl, if I take away C6H4 for my para disubstituted thing, I get CH3Cl. If I spend the C and the H3, that just leaves the Cl. And I have something that pushes electrons in, the methyl, and I have something that pulls the electrons out, the chloro, which would make the gap in my para disubstituted doublet of doublets, right here, be much wider in the middle than it is between the 2 outside bands. The coupling constant in the middle is significantly larger than the coupling constants at the edges. You may be able to draw that in Spartan. I'm not sure that it would give you an answer, but you can have a try. Yeah. It's the doublet of doublets. And then there's a singlet for the level. So this software might even be smart enough to say the difference between that one and that one. Okay. That's a success. It really works. Try C. C. C is not dissimilar to A, but it does require knowledge. Well, you can figure it out as long as you know that carbon always has to have 4 bonds, oxygen always has to have 2, hydrogen always has to have 1. But it's a type of molecule that we have not done yet in organic chemistry 2. It's a class of molecule that we will be doing soon. A week, 2 weeks from now. After all the aromatic systems, we're going to do carbonyls, aldehydes and ketones, and then from that we're going to do carboxylic acids and their derivatives. You can, yeah, no. You can join in. They're using the software, so it's best if you come around. And we're working on and they're doing
Is this what we're doing for the lab, or?
yeah.
Oh.
And then we'll be wrapping up.
Okay. Oops, sorry.
Process of elimination, if you figure out what some of the fragments are, then everything else has to fit. Just make it fit.
I just realized what time
Yeah.
it is.
Did the clocks go back in your house? When do the clocks go back? I don't know. Or do they go forward? I don't know.
I don't know.
I'm
we lose an hour.
a grown man and I don't know whether the clocks go forwards or backwards. Yes, so.
So it's,
Do you remember NMR?
I do. But I think I would have to go over step by step.
Yeah, yeah.
So start with this one?
So we just did that one.
Okay.
It turned out to be this, but A and C are very, very similar.
B and C,
because-
or?
No,
A and C?
this one, see the shape of that?
Mhm.
no, it's.
It's like this also. It's a doublet with a big space between them. It's a doublet and then a space and then another doublet. This is because it's a para-disubstituted benzene, which means it's a ring of 6 carbons with four hydrogens, and then there's a group at the top and a group at the bottom. And if the group at the top and the group at the bottom are very different from one another, then the gap between them gets larger.
Okay.
And they kind of have any neighboring.
And the integration underneath the signal tells you how many hydrogens gave rise to this signal. So these four hydrogens
There's only 2 and 5.
belong
Yeah, because
to this fragment right here. And then what we're going to do is figure out what goes in the boxes. I'm going to roll the boxes in. I'm going to figure out what goes in there.
That's where the paramedic street area that does a double.
So there's a box here, and there's a box there. And I know that whatever goes here and here are two different things, because this
C6H4 and subtract that, so you get C6O2.
gave me a doublet of doublets with a very, very big gap from it. What's the chemical formula of the molecule I'm looking for?
Of A or B?
This is now C.
C9H10O2.
So I'm looking for C9H10O2. This right here is C6H4. So 4 hydrogen signal. And then I have a 3 hydrogen signal. And another 3 hydrogen signal. And they're both singlets. If a signal is a singlet, what does that mean? It has no hydrogens as neighbors. Okay. And it has 3 hydrogens in it, so it means this is it's a methyl. That's a methyl. And this is a methyl. But they're different types of methyls. What was the shift on them? One of them is at 2.5, and the other one is at 4. So the chemical shift of this. Of these two, which one's nearest electron withdrawal? Severe electron withdrawal is more likely to be because you are directly attached to an electronegative atom. Are there any electronegative atoms in my formula? I got 2 oxygens. All right, so let's piece this together. C6H4, here's what I know. My molecule is C9H10O2. If I subtract C6H4 from that, it equals 3 carbons, 6 hydrogens, 2 oxygens. So I have 3 carbons, 6 hydrogens, and 2 oxygens. I know where my hydrogens are because they're here and here. So that's a pair of methyls. So if I take my C9H10O2 and I subtract the C6H4, the CH3 and the CH3, that leaves me what exactly? Not just the 2 oxygens. It leaves me a carbon and 2 oxygens. Carbon always has to have 4 bonds. Oxygen always has to have 2 bonds. This is just like at some point in chemistry 1, we put the pieces on the board and told you, go ahead and stick these together. Here are your pieces. Well, it could be that. Make it work. There are two possible, what?
Yeah, I know. I couldn't figure out where that last carbon was, so I put it right there.
Why don't you just have the oxygen be doubly bonded to the carbon instead of making it?
And where would this option look like?
I had a crazy
Just
molecule too.
There we go. As I see it, there are two possible answers. And this is where the software might jump in and help you. The correlation table on the back page is here to help you. If I put one of the methyls directly attached to the ring, then both of my oxygens have to be in the other group. Well, that's not a problem at all, because that is an ester. You can do that. The other possibility is this. And the way to know what it is and what it is not is to look at the correlation table and figure out where would an ester show up, and then where would a toluene show up. So, where would a methyl attached to a carbonyl show up? Where would a methyl directly attached to an oxygen show up? Where would a methyl attached to an oxygen that is part of an ester group show up? Where would a methyl that is a toluene show up? And you can either pour through the correlation table, or you can look at the software and drop both molecules in and see which one of them is the best fit.
It's not. Esters.
Yeah. So, yeah, that is, there's no reason why this should be. And then, of course, so we can't see the other one. How about if I did methoxyacetophenone? Back. That's the methoxyacetophenone. It's the one on the left. And it has the big, broad, doublets, two singlets. One closer to 2 and one closer to 4. Okay. So 3404 we'll do some theory on NMR tomorrow. The theory that we'll talk about will be deeper than the organic chemistry's theory, and after we're done with this kind of, hey, just use this as a structure determination tool, we're going to look at different nuclei. We're going to look at some carbons, maybe some phosphorus, and then we're going to do it in 2 dimensions. And there's a couple of different two-dimensional techniques that are subtly different from one another and give very, very detailed information.
And this worksheet too.
Yeah, we'll.
Because what did y'all do during class? Was it that first page?
So we had a quick discussion, run through of chemical shift, integration, and multiplicity, which is a recap from organic. But we just used this time to start working through this worksheet, so there was no real class. Plus, it's on the video, and the video will go up.